Once again, thanks to all of you for organizing this, for inviting me. It's a privilege to be here today, and I hope this session is worth of your time. Basically, we will be speaking about how artificial intelligence, machine learning, deep learning is enabling what is called Software 2.0. So, firstly, the acknowledgements. I would like to acknowledge all my colleagues at Ericsson. I belong to Ericsson Global AI Accelerator in Bangalore, India. To my colleagues and to Saurav, the manager of our team, who helped put together these slides. So Aishwarya did introduce me, but I'll just take a few more minutes to give a bit more details about myself. So my background is in computer science, and my PhD specialization was in software engineering. I started as a software engineer and senior software engineer long ago in Siemens. I think now it's called Nokia. Then I went to the US for my PhD. So I earned my PhD in computer science from the University of Delaware in USA. Delaware is the state of, I think, their current president, Biden. My PhD dissertation addressed the topic of code summarization. So I was the first to propose techniques using heuristics, program analysis, and AI to automatically summarize source code in the form of comments. So after my PhD, I was a research scientist in IBM, IRL in India. And then I joined Ericsson as a principal data scientist with the view of bringing AI to software engineering. I have about 24 publications, research publications in leading conferences, and about 17 US patents. Both the publications and the patents are mainly in the area of software engineering and using AI to solve these problems. So that's about myself. Today, is this slide visible? Is the slide movement happening seamlessly? Yeah, okay. So we will talk about how software engineering is getting revolutionized, especially with the use of AI. AI is kind of ubiquitous now. It is used everywhere. How is it being applied to software engineering? How software engineering itself is changing? Is it changing for the better? I think so, yes. But how are people impacted by this? What kind of roles are getting affected and so on? And how are organizations leveraging AI in the software lifecycle based both on my experience at Ericsson, IBM, and other companies also, and popular AI-driven use cases in the software industry. Some leading companies like how Google, Facebook, and IBM are all using AI to improve, use AI in software engineering. So the industry is transitioning to the software 2.0 state. Basically, what we had up until now or a few years ago was what we call software 1.0. It was mainly human-driven programming, rule-based, reactive, and of limited efficiency. I won't say it was bad, but it was not highly efficient. The trend, as McKinsey has identified, is software 2.0 is the future trend, where 2.0 is machine-driven, machine intelligence, artificial intelligence. It is largely going to be, the hope is it is going to be self-programming. It will leverage AI. It will be proactive instead of being reactive and highly efficient, kind of the opposites of what we are doing now, but with a good view. Currently, we are at a machine-assisted decision-making state by the AI. We are not really in software 2.0. We're somewhere in between, moving towards 2.0. It's more of a predictive model and continuous efficiency improvements. So let me just step on to the details of this. So we are moving towards 2.0. Initially, when I started programming, say 20 years ago, it was software 1.0. And before that, I would call it software 0.0, meaning it was all manual. So for what do I mean by 0.0? For example, consider making a fixed deposit in a bank. About 25 years ago, our parents' generation and all, they would go to the bank, some official at the bank, they would enter our name and other details and take the deposit term, like whether it is 1, 2, or 3 years, consult some reference manual for the interest rates, use a calculator at best to find the interest rate, and enter all of these in some ledger book and give us a receipt or a voucher. So everything was manual, perhaps for the use of a calculator to calculate the rates and so on. So then we moved to 1.0, where parts of these processes were automated. For example, we would have some user interface, graphical user interface, pioneered largely by Microsoft and made easy to use. We could enter details like our name, age, and all those things. Some subject matter expert would then tell us about the requirements and provide information on, say, this is the interest rates, and we would code it using a language like C or C++. We would have a lot of these if-else or switch case statements. It was largely rule-based. For example, we would have code like this: if term equal to 1 year, interest rate equal to 5%. If term equal to 2 years, interest rate equal to 5.25, and so on. If the interest rates changed, say, we would modify the code. If there was a new term like 1.5 years, we would have to add an additional if-else or an additional switch case statement. All of this could lead to bugs, like you could miss a break statement and so on, so the control would flow through. This was all a perfect recipe for some kind of a buggy code leading into production. You have to test it very thoroughly, of course, and so on. Now, object-oriented programming languages like C++, Java, C# to a certain extent, they help rectify the problem somewhat. They ameliorated the problem somewhat, not fully, because the whole protocol of per se was not changed. The rule-based reactive programming environment was not changed. What they did was, instead of having one file with a lot of if-else or switch case statements, we would have some kind of a base class called, say, bank operation, and you would have methods or virtual functions like deposit. So if we wanted to add new functionality, instead of adding a new switch case or a new if-else, we would perhaps add a new derived or inherited class, and that would make the code more readable, more robust to changes, but that was about it. It was not really changing the paradigm as such. It was changing the way we would implement the things, not changing the paradigm per se. Still, it was rules-based. So the paradigm of implementing these rules was changed from procedural C to, say, object-oriented programming. It did improve the situation, but it was still, fundamentally, it was still rule-based operations. So software 1.0, as I mentioned, was reactive. We would react to situations, whether it was a bug or a new feature. Rule-based, reactive, human-driven, limited efficiency. 2.0, I think, tries to be the opposite of the above. So for example, instead of some subject matter expert or somebody telling us, instead of we manually coding interest rates, etc. So given a lot of these data, we have maybe millions of deposits in banks. So we know the amount of money invested, the term for which it is around. This is just an example. Here we probably don't need this, but this is an example. AI can deduce the interest rates. It can learn the interest rates. Instead of reacting to situations like, say, adding a new feature, for an app on your mobile, we can analyze the Google Play Store review comments, and we could use some kind of, say, unsupervised learning or clustering means or any kind of clustering algorithm, and we can find that a lot of users are requesting a new feature and proactively implement it. So I'm not very active on social media, but if you see, and I think on Twitter, one of the frequent requests is to add an edit button or an edit functionality. Somehow, for some reason, they till recently at least, they had not implemented it. But you could look at all the Play Store review comments, and by grouping the comments together, you could find out that many users, probably thousands or even millions, are requesting for this particular feature. So this is what we call by being proactive. We know that people are requesting for this, and so we kind of can code for it as well. So from the comments, we can also perhaps deduce that there is a bug somewhere. Somebody might have said, if I do this particular upgrade to this particular version, I'm unable to, in Facebook, for example, they might say I'm unable to upload photos. So they can deduce the bug and be proactive in finding the bugs. And if we have these logs, we can, for example, do anomaly detection to proactively find bugs and fix them. So we need not wait. In the older paradigm, it was all like we would write the code, somebody would give us the requirements, we would write rule-based code, we would send it to testing, wait for the testers to verify the software, get back to us with their feedback, and so on. So all of this, we can be very highly proactive. We can look at the reviews, we can use log anomaly detection, so on, and we can be faster in our responses. So this is where the trend is moving. We are not really there yet. It's not self-programming. Like, given that there is a request for this feature, ideally what might happen is this feature gets coded based upon other examples that the machine has learned, but we are still not there yet, but we are moving towards it. So this is about the moving from software 1.0 to 2.0. We are somewhere in the middle. I'm glad to say that I think we are moving towards that direction. How long it will take or whether it will even be realized, it's a bit hard to say, but we are moving towards that. Now, the whatever it is, whatever we call it, 1.0, 2.0, or perhaps later on 3.0, the expectations have remained the same over the years. The expectations from software. We want faster development, we want better quality, and we want lower maintenance costs. So I'll explain all of this in detail. But basically, the expectations, whatever be the numbering system that we are using, whatever version of software we call it, the expectation has remained the same. We want good quality software. We want it to be developed faster, and the maintenance costs, adding, fixing bugs, adding new features, refactoring, so on. We would like it to be not very high the cost. So this is that French saying, more things change, more they remain the same. Say, Ola or Uber or any other cab aggregator, they have a bug in their app. They can't wait for days together for the bug to be fixed. They expect a fix within a few hours maximum. But the situation was the same even many years ago. I don't think even at that time customers would wait for days together for a bug to be fixed. So let's say a bank's software had erroneous interest rates. It would require a fix as soon as possible. Also, the emphasis is on faster development of a new feature, faster fix for a bug, better overall quality. By quality, I use it as an overloaded term, denoting the quality of the overall software and also internal quality. How easy is it to maintain the code, understand to add new features, fix bugs, and so on. But also, the emphasis has always been on lower maintenance costs. So nothing really has changed in expectations. What has changed is how we manage to achieve these expectations, especially using AI. How we manage to achieve these expectations, essentially. So consider testing, how it was done previously and now and in future. Previously, it was perhaps we would execute all the test cases and perhaps select or prioritize a subset using the domain expertise of the experienced testers. Now we use AI. So, for example, one work that I will talk about that was done by Facebook and another company was they're using AI to select test cases, maybe based on code differences, and so with pinpoint accuracy, select the relevant test cases, or use the previous history of test cases, what has failed, what has not, and certain features of the test cases to kind of output a probability score of how buggy or how likely this test case is likely to fail, and then select test cases, a subset of them which are more prone to failure. No use selecting test cases which for a quick regression or a quick check. We don't want to select test cases that invariably pass, but we want to select test cases that can reveal faults. So we using AI, we can do these, and that is what I'll speak about in one of the works here. So in this slide, we'll talk about how organizations are improving by using AI in software engineering process. We have broadly different phases. We have development, we have quality assurance, we have deployment, and we have maintenance. There are other phases as well, but we can broadly categorize these as the four multiple different phases of the overall software development. So in development phase, to manage the software complexity, as you know, complex software is more prone to bugs and so on. So that for that AI is being used for developer assistance. I'll speak more about it in the next slide. For code completion, for comment generation, logging statements, and so on, AI is being used. And this is something that has come recently, fairness of models. For example, if a lot of companies are using AI models, for example, a bank or targeted ads by Google and so on, here we need to be sure that our models are not biased. For example, a bank must not turn down an application based on, say, gender or race. So how do we ensure that the model that we are building or developing is fair? It is not biased towards one set of group or biased against another set of people and so on. So that is something that AI is being used for. In terms of quality assurance, for the different facets of quality assurance like code reviewing, static analysis, testing, all of these has benefited by using AI. Organizations have used it also to make our code more regulation compliant, privacy, security, and so on. And then in deployment, there is AI has been used for continuous integration assistance, seamless integration into the continuous integration, continuous development pipeline. And in maintenance, for example, we have different phases of maintenance, what we call corrective maintenance, where bugs are fixed in response to bugs being reported by the users, or predictive maintenance, where you predict beforehand some problem is going to occur. Like I was talking about this anomaly detection. We analyze the logs and we we feel that there is a problem. So this predictive and corrective maintenance have benefited by using AI. Then there is the concept of tech debt, where we postpone certain decisions because it is more optimal or easier to do something now, but this will incur a debt that must be fulfilled or returned in future. How to automatically detect these debts, like obsolete comments, for example. So this is a perfect example of a tech debt. How to automatically detect them, how to fix them or remove them, so on. So these are the different areas that AI is being used. And so the popular AI-driven use cases. So for in development, as I was speaking about, we have variety of coding assistants. For example, we have assistants that will help you given a set of requirements. There is AI-based software that will tell you which kind of APIs should you use from. Typically nowadays, nobody writes all their code on their own. We use libraries. So which APIs? These libraries have hundreds and thousands of APIs. Which library should be used? Which API should be used? There is assistance for this. Then there is code generation both from natural language documentation and code completion. So here, as I'm typing the code, what is the next token or the API to be called, or how it could range from simple semicolon, using a semicolon at the end of the statement, to actual tokens. Like if I'm writing a for loop, the next token will be, for example, an int I equal to 0, and so on. There is also work on comment generation. When I did comment generation, summary comment generation, we used heuristics. But now AI can be used, because we have this. One of the greatest things about the software is like we have a lot of this open source software, previously on SourceForge, now on GitHub, and so on. Many of these have good comments written for functions and methods. So using this as a training sample, as a large set of training examples, using both deep learning, transformers, all these technologies, we are now at a state where we can generate very good comments, summary comments, and so on. Also, logging statements. As you know, logs help very much in debugging your software code. So we want to know the challenges here are where to put the logging statement, or what kind of information to reveal, and so on. What level of information should be provided, and so on. So for this also AI has been used. Again, learning from the existing examples. So in testing, we have a lot of work on test case selection and prioritization. One of this I'll speak about in the next few slides. Then in testing, we want oracle generation, like the system outputs certain thing. How do we know that is the correct answer or not? If it's a simple thing like 2 plus 2, yeah, we know that 4 is the answer. But in many cases, we don't know. So we need an oracle. Oracles typically require experts. Can we kind of minimize the role of experts, because that will save us substantially. So can we generate oracles? Code reviews are being done automatically using AI. Then static program analysis. One of this I'll speak about. This is one very interesting thing, because this is a core computer science compiler area. Now AI has been applied to this as well. And testing on different configurations, like with Ericsson, where we have different hardwares, how to choose the correct hardware to test. We cannot afford to test on all hardware all the time. And then in deployment, there is work on build optimization, figuring out how much time a build takes, and so on. Avoiding so-called brown builds, meaning builds that fail. So that will cost us a lot. And then finally, in maintenance, we can have AI has been used for anomaly detection, bug localization. When a bug is reported, which source file has the bug. In modern software, it's not unusual to have hundreds or thousands of source code files. So in which particular source code file is the bug present, or even more fine-grained, which method or which function or which line has the bug. So this kind of work has benefited by using AI. Then automated program repair. Once the bug has been reported and localized to a certain source file, can we do an automatic fix? For example, if it's a division by 0 or a null pointer, perhaps we can add a null pointer check, or check that the denominator is not 0. But even more sophisticated repairs for bugs, they are being done using AI. Code refactoring, this has been going on for many years now. AI can help us detect, suggest which method should be refactored, what are the characteristics of maybe a method which has too many lines, or a class which has too many functions, and so on. And then modularization, or what's called app modernization. The trend nowadays is towards having these microservices, not monolith web applications, but smaller microservices for scalability, reliability, and so on. How do we automatically break down a monolith into these microservices? Even here, it has benefited by using AI and so on. So AI has been used across the board. Like I said before, it is pretty ubiquitous, but in various other fields, in medicine, so security, and so on, I cannot think of a field where AI has not been used. But even in software engineering, the entire spectrum, left to right, of software development, AI has been used very effectively, and we'll see some examples of this at leading companies in the next few slides. And depending on the time, I don't know if I can cover all these 4 different use cases, but I'll try to cover as much as possible. So there is a test selection work using machine learning from Facebook. Then Google has done some work on smart builds, again using machine learning. IBM, there is work on more precise static analysis, and within Ericsson, another group has done work on automating the code review process. So depending on how much time we have, I'll try to cover these. So all of these use cases are essentially, so far I was talking more at a theoretical or at a slightly high level, very abstract. These are the practical demonstrations of how AI is helping us to move from the current one dot. We not be stuck with terminologies, the current way of doing things to the next way or the new way of doing things. So a lot of these examples, hopefully, in my opinion, they will, but hopefully you will also feel that how AI is helping kind of, I won't use the word revolutionize because that's a big thing, but how it is helping to transition to the next phase to improve things essentially. So this Facebook's work, this was published at, there are some leading international conferences, research conferences, International Conference on Software Engineering, Foundations of Software Engineering, and so on, where academicians present research work, and also industries are encouraged to submit their work. There's a separate track called the industry track, or something called Software Engineering in Practice track, where they're looking for more practical things which are actually deployed and used in their day-to-day affairs. So Facebook has done this work. This was, I think, published 1 or 2 years ago at the Software Engineering in Practice track of the International Conference on Software Engineering. So I'll just start with some background on test selection. So modern software apps, they typically have thousands, and in fact, I think they have millions of lines of code. This is perhaps unavoidable. We can perhaps reduce a few thousand lines, but that's about it. This is unavoidable. And to test these apps effectively, we need hundreds and possibly thousands of test cases. And these are developed actually by testers. All the companies have huge efforts invested in testing. Now, code changes are made frequently to the apps for a variety of reasons, to address defects that are reported from the field, from the users, to add new features, to perform internal maintenance, refactorings, to enable the code to be read better, understood better, and so on. So, for example, Google itself has said in one of their papers, they see about 100,000 commits every day. 100,000 commits. They have a monolithic code base and about 100,000 commits every day. Now, the goal is to ensure that this newly added code that I add, it does not break existing functionality. So how can I ensure that? Ideally, I'll have to run all the test cases, but it is extremely time consuming, as you can imagine, and infeasible to run hundreds or thousands of test cases every time a code is modified. 100,000 commits per day means almost every minute there is something going on, or probably multiple commits per day. We simply cannot run thousands of test cases every time the code is modified. So what is needed is a way to automatically select test cases, a subset of them that will reveal the faults and ensure that the existing functionality is not broken. So typically a subset of these overall test cases are selected and they're run to ensure that the code modifications have not led to any loss of existing functionality. So we call this regression errors. Unfortunately, the term regression is a bit overloaded here, because even in machine learning, we have these concepts of linear and logistic regression. Here, regression is the classical English term, meaning to go back. That means some functionality has been lost. So such test cases are often selected manually. And like all manual processes, are tedious, they are time consuming and error prone. Now, if I select fewer test cases than optimal, what can happen is it can lead to bugs not being detected. in our testing and then escaping into production, meaning the final users or in the field, the users will see it, which is not good at all, especially for companies like Ericsson and all, where we have service level agreements with our customers that there won't be the bugs and so on. We don't want the bugs escaping into the field. We want bugs to be detected within our environment itself. But if we select additional test cases, then optimal, it leads to additional time. In the degenerate case, we can select all the test cases, but that's simply not possible because we have thousands of test cases. So this leads to additional time for test case execution and delays on the CI/CD pipeline, the feedback to the developer once the bug is detected. Now, that is not the end goal of that. We want the bug to be fixed as well. So this whole process gets delayed. So we want to select the correct number of test cases. And we could do this using static analysis. We, for example, use the diff to select relevant test cases. Now, what happens is, this is not AI, this is just pure program analysis. But scalability issues are there when there are large code bases like that at Facebook. And one might opt for less precise analysis, but that leads to loss of precision. And in Facebook, in this paper, they say they have their control flows across multiple languages. Their code base has multiple languages. So analyzing these is very challenging. So static analysis, which was not using AI, which was based on analyzing the source code and using the diffs to select relevant test cases, is not really applicable or cannot be applied. With dynamic analysis, what happens is typically, again, this does not use AI. You run the test cases, you get logging information. Hopefully the logging is at sufficient granularity. If it is not, we have to instrument it. We collect the execution traces and then analyze which test cases must be run. Again, this requires recording huge amounts of program execution traces, which is not feasible. So what they have done, they try to use something called build dependencies, using information extracted from build metadata to determine which test cases to run on a particular code change. But by analyzing these build dependencies between units of code, one can determine all the tests that transitively depend on sources modified in that code change. So here is an example. Need not really go into this in too much detail. At the top, we have these circles. These are the test cases. We want to select a subset of them, and then at the bottom, the rhombus or the diamond shape we have, these are the source codes that are modified. Using build dependency, they say they again cannot select optimally. They still end up selecting more test cases. So what they have shown is the existing non-AI techniques don't work well at all. So this approach has significant shortcoming. It says the test is impacted more often than is actually necessary, and it would cost many as quarter of all the available test cases to be exercised. So that is not acceptable to them. So what they have done is they have reframed the problem. What is the probability that a given test finds a regression failure with a particular code change? Remember that the code change is what is triggering these tests to be run. So what is the probability that a given tests find a regression failure with a particular code change? So if we estimate this, we can make an informed decision to rule out tests that are extremely unlikely to uncover an issue or that won't reveal a failure. So this is a departure from the conventional test selection, and it's an efficient way. That's what they claim. So what in machine learning, now you can see the AI coming into it. A predictive model was built that estimates the probability of each test failing for a newly proposed code change. So instead of defining this model manually, it is built by using a large data set containing the results of tests on historical code changes and then applying standard machine learning techniques. So here is the approach. There is a training phase. We have the code changes, we have the tests, whether it passed or failed. It feeds into the test selection model. And then at prediction time, we have a new code change. The test is there, the test selection model, and then it outputs the probability of failure. And we can then sort in descending order and select the top, which have a higher probability of failing. So each new code change, now it will always be slightly different from the previous ones. So the model cannot simply compare a new change with a historical one to determine which tests are worth running. So an abstraction of the new change can be similar to the corresponding abstraction of one or more of the previous code changes. We need to make an abstraction. We can't simply use the new code change literally. So what is done here is that during training, the system learns a model based on features derived from the previous code changes and the test cases. Then when the system is analyzing new code changes, they apply the learned model to a feature-based abstraction of the code change. So for any particular test, the model is then able to predict the probability of detecting a regression failure. So here you have the code change and test target on the left. we have different features here, like for example, size of the change, the number of files and the lines modified. Larger changes are more likely to fail. Something like code info. All of this, it's just for, you don't need to really know this. This is an example, like history of test recent runs. History of recent runs is a good predictor of how likely the test is to be broken, the topology of the build, evolution of the code base, and so on. So these are different features that have been extracted automatically from the source code change and the test target. And then these are used to build a predictive model. So the first feature, for example, hot portions of the code or size of the change. Larger the changes, large changes are more likely to introduce breakages in the code. So that is one particular feature. For example, code ownership, who has owned the code, or fewer developers modifying the code. All of this are features in this model. So this is, as you can imagine, there is some manual effort here in determining these features, but these are extracted automatically and these are learned. We think some of these may be important. The machine will learn what exactly is important. So for the actual model, this decision tree was used. This is a gradient boosted decision tree. So other ML algorithms could be used, but they use the decision tree because they're explainable, easy to train, and part of their infrastructure already apparently. So with this, the model analyzes a code change to find all potentially impacted tests that transitively depend on the model files, and then estimates the probability of detecting a failure. So based on this, the tests are selected that are most likely to fail for a given code change. So here, what they say is, in that particular example, the older way, the non-AI way, would have selected this 1, 2, 3, 4. 5 and 6 would not be selected, the test cases, but 1, 2, 3, 4 all would be selected. But what they really wanted was to only select 1 and 2, because this test case 1 had a probability of 0.99 of failing. Test case 3 had the next highest probability, 0.32 of failing. So they select these two, and they say this is what they say is their optimization using AI. Using this machine learning from the past historical data, they're able to optimize this process. This is just an example. In reality, we have shown only 6 test cases here. In actuality, there will be thousands of such test cases, and they end up selecting only a few hundreds of them so that they can run within the time limit. And they say this, they have deployed it for more than an year, and it has enabled them apparently to catch more than 99% of all the regressions before they're visible to other engineers in the main branch. And they say they are able to get away by running only a third of all the test cases. Now that is pretty impressive, because if you have thousands of test cases, running only a third of it is significant savings of time. You don't have to run the remaining 2/3, and yet you are able to uncover 99% of the faults, 99.9% of the faults. So that is really impressive, and no wonder they're using it. So they say this has allowed them to double the efficiency of testing infrastructure. So Facebook has, to put things in perspective, has a variety of automated tools to deal with different aspects related to code change. In this paper, they covered test case selection. They have a tool for code analysis, suggesting a patch or a code fix snippet, generating new test cases that reveal the conditions under which a mobile application would crash, and so on. So this is kind of their life cycle. So this is typically more than all the particular details of how this was done. What I want to emphasize is this particular testing or fixing the bug and so on. All of this would be done manually before, or using some kind of automation like static program analysis and so on, all of which would not scale. But by using AI, they have managed to kind of achieve their goal of running fewer test cases in the regression, 1/3 of the test cases, and uncover more than 99% of the faults. So AI is really helping them in this process. So now I'll move on to another example, use of AI to improve the process in Google. So Google, like I mentioned before, has a monolithic code base, and it grows rapidly with more than 100,000 code submissions per day. To make sure that these changes do not break, they have a continuous integration in process. So for each code change, the CI system first uses the build service system to build the affected libraries and binaries. Then it runs the affected tests to check if the built libraries and binaries are working as intended. They use this tool, it's also an open source tool, I think, called Bazel, to build the libraries and run tests. Bazel takes as input a set of build specification files that declare the build targets and what needs to be built, like a library or a binary and so on. and also a test target. What tests are needed to be run if a code change breaks the code base and so on. So essentially, this is all about build, unlike the previous one where it was more about testing the Facebook application. So what happens is, as the code base grows, each change may affect a lot of targets. So a code change on a common library, you may be familiar with this library called Goa. It can affect many Java targets. If they change the C++ compiler itself, it can happen. It will affect all their C++ targets. So their problem is they often end up having to build millions of targets at once. So running a large number of these targets, even for Google, which has humongous capacity in terms of servers and so on, even they face this problem that a large number of these targets, it causes out-of-memory errors. And they also have this problem that if they're executing too many targets in a build, they have some time limit specified, that like they want this build to be finished within a certain deadline, say maybe 30 minutes or so, the entire build process, building it, testing it, certifying that there are no bugs, move on to the next stage. So they have this problem called deadline exceeded errors as well, because they're simply executing too many targets at one go. So this is really interesting and illustrative, because with Google, we think that they have practically infinite almost infinite capacity servers and so on, and yet they face these problems. They have so many targets to build, they run out of memory, it takes more time than they intended, and they get these errors and so on. So they wanted to what they wanted to do was they wanted to group these build targets. Not all targets take a lot of time or a lot of memory, CPU, and so on. Some targets, like for example, like I said before, if the C++ compiler has changed, then it will take the build might take a long time. Whereas if I've just changed one line of code, maybe the build will not take so much time. These different targets, they want to intelligently group these targets. They want to group certain what we can call heavyweight targets that take a lot of resources with a number of lightweight targets that don't take so much resource. So they can intelligently then assign it to different servers. Each server will probably have one very long-running memory-hungry build with numerous smaller targets that don't require so much memory or compute power. So like this, they want to intelligently assign it to different servers they have. But what is the precursor to that? They need to know how much memory a build will take, a build of a target, how much time would be taken by that build. And how can we do that? We cannot simply, it's not possible for the 100,000 targets for a human to compute it or to know it off the top of his head or know it at all. So what they did was they used AI again, machine learning, a relatively simple linear regression model that will predict the peak memory usage of a build, how much memory would be used up, how much time it would take. So this is an excellent example of build bringing in AI or machine learning to hitherto normal computer science software development process of building. Building is a ubiquitous activity. It's done almost millions of times every day across different companies. But here they used AI to predict the memory usage of the build and time taken by the build. So using this, they group targets such that the out of memory and deadline exceed errors do not arise. So they used feature engineering. Feature engineering means deciding which features could help in these predictions. For example, the priority of the build, the command name. So if it's a C++ compiler, then probably it will take more. Whereas if it's some other just running a test case or a code review, then it may not take so much time. The user, that might be important because certain users might give rise to heavy builds, the area, a lot of these things. Like so these are again illustrative. I don't want to get into details of this. They use these features and they built a regression model that was fairly accurate and that helped them predict the time taken and also the out of how much memory it would take at and that they could use to predict to smart batching or grouping of these targets. So this is a excellent example. I felt, at least when I read this paper, of using AI for a relatively mundane or a very common task like building. I had not thought that AI could be used to improve this process as well, but surprisingly this was used, and at a company like Google. And in fact, I would never have thought that they would run into these kind of issues, that they would have out of memory, they would simply not have the server or the computing resources to build their targets. But it does happen, and for that they came up with a very interesting solution. Importantly, more than the fine-grained details of what features were used and so on, to me it is illustrates that AI, even relatively simple AI, linear regression and all, has been around for 40-50 years now. It is not a new phenomenon. This machine learning and AI being used to improve the build process, that was to me very interesting. How much time do I have, Aishwarya? At least 15 more minutes?
Yeah, definitely. Please go ahead, Giri.
Okay, so let me. So here, some of the interesting things are how still some manual effort is involved in building these models. For example, it requires the experts, the build experts and so on, to tell these features may be important and these are not important. But the fact that they've come up with this, to me, was very interesting. Both Facebook and Google. For testing, it's kind of relatable that yes, there are thousands of test cases, and so we need some tool to automatically select a subset of them and so on. But here, for a build process, to use this was really very instructive and very useful to know for me. So next, I'll speak about again another a work from IBM. This was also, all of these, even the Google's paper was at I think a couple of years ago or last year at this international conference on software engineering, the Software Engineering in Practice track. So this is another work from IBM. They use differential analysis for static program analysis. So I'll just get into what this is and so on. This will require some details. Static analysis of code. Basically, I'm not sure how many of you have the background. Static analysis of code is kind of the compiler plus stage. We write code. There is a compiler that analyzes the code, builds the final binary, the machine, the zeros and ones that the computer finally understands. So that is the compiler part of it. Static analysis is kind of embedded in that, where it will look at your code, not with a view to building the binary, so the runnable binary. That is the job of the compiler. But in static analysis, what we want to do is we want to see if there are potential problems. For example, it could so happen that I'm doing a division, but before doing the division, I may have a calculator program or some situation where a division is required. And in this process, while I'm doing the division in the code, I'm not checking if the denominator is 0. So if the denominator happens to be 0, the CPU will throw that divide by 0 exception, and we don't want that to happen. Rather than wait for the system to run and reveal the fault, or for it to be revealed during testing. Because in testing, it is a hit or a miss. We may or we may not, because that situation of division by 0 has to occur. What static analysis tries to do is it tries to preclude these problems by looking at the source code and telling you, hey, perhaps you're dividing by 0. Similarly, a more common problem is the null pointer. We have a pointer, especially in C or C++ kind of programs. Even in Java, it could be possible that there is a pointer or a reference which has not been assigned properly, and which will then, upon dereferencing, will throw the null pointer exception. So static analysis tries to do this. It is very complex. Some of these, what I was saying was very simple. It has to analyze all the paths and so on. So what it does, static analysis, unfortunately, it generates many false alarms, false positives, because it uses approximation heuristics that required for scalability. So if you remember the Kernighan and Ritchie's old C programs, they were fairly within one page they would fit in, and for those kind of programs, static analysis tends to be perfect. But for modern software, which runs into thousands and millions of lines of code, static analysis does some approximations which leads to false alarms. So why this happens is it has to model all the possible execution behaviors, and as it suffers from what is known as the state space explosion problem. Exponentially, the 2 power n, the number of paths it can grow, and if you have 10 different paths, you have already 2 power 10,024 paths, and with many more paths, it can just blow up the state space. So it has to model all these possible execution behaviors, and it simply cannot even finish in on time. So to handle these industry scale programs, what static analysis of code does is it takes very aggressive approximations, and so that it can complete, or it is feasible to even do it. Otherwise, it will run for days together, which we cannot afford. If we had to run static analysis for days together, we might as well as test and will release it to the field and then hope that the bug manifests itself in the testing. So what it does is, to sacrifice the precision for scalability and speed, it does a lot of approximations, something called path-sensitive analysis. This, the path that is taken, for example, if you have an if condition, within that a for loop, within that an if, you already have 2 power 3 combinations here. So all of that, if it tries to model it, it will blow up. So the path sensitive analysis does not scale well on large programs when there are too many path states or reasoning about path constraints. Path insensitive analysis is done that ignores these path conditions and assumes all paths are feasible. That's used in practice. So this introduces false positives, meaning what do I mean by false positive? It can say that, oh, hey, there is a potential division by 0, but it could so happen that there is when I read the code thoroughly again, I find out in one particular path there is the path that is invariably taken. The denominator is assigned to, and it can never be 0, or that pointer is not null. So this requires extra effort for me, for the developer, because the developers now have to go through. It's like the boy who cried wolf. A lot of these false complaints. You tend to suspect this tool, and you won't take the real errors at all at value, because you might miss it. If there are 10 for static analysis, 10 potential null pointer exceptions it reports, and 9 of them are false alarms, it is possible that I missed the 10th one, because it's natural, it's human tendency. So this is an example of, in this particular paper, they used a static analysis tool called Infer to report a bug. So as you can see here, the details are not important, but line 385 here, they're saying this pointer GTR is potentially null. This was assigned at line 382 here, and this report says that this pointer could potentially be null. We would have had to had an if GTR not equal to null kind of check. So this is an example of a true positive, but unfortunately, like this, there could be many false positives as well. So we want to automatically, how can we do it? Automatically fix these false positives. So the goal is to label the issues reported by a static analysis tool as a true positive, that is, it's likely to be an actual problem, or a false positive, it's unlikely to be an actual problem. So what they do is we could have humans manually annotating, going through each of these and saying that this is a true positive or a false positive. But this is simply not feasible in the long run, because these tools, they report thousands of such problems. So it is, and anywhere the human steps into the loop, as I mentioned before, it is tedious, time consuming, and error prone. It defeats the whole purpose of using these tools. So a very intelligent idea was developed in this paper. What they said was they gathered pairs of code commits. Code commit is where you kind of submit your code to go to the next phase, to be built to the binary and so on. So they gathered pairs of these code commits, version I and the next version I+1, and run static analysis on both the versions, the before and the after versions. Now, if the issue that has been reported, like in the previous slide, we saw some issue being reported, line 385, it said there's a potential null pointer. If the issue reported in the before version is not reported in the after version, so it's very likely that it was an actual issue which was fixed by the developer. So maybe here in the previous slide, we saw that GTR, that pointer, it was reported in version I. In version I+1, if I run the tool again and that is not reported, maybe the developer added that null pointer check. He took care of it, he fixed it. So then what it tells us that it was a genuine issue. But if the issue reported in the before is also reported in the after version, it is possible that the developer has not fixed it, or it is also very likely that it was not an actual issue, it was actually a false positive. So this is a very clever intuition that is used, and using this, they generate a labeled data set automatically. That's the crucial part here. So we get a set of automatically a set of data that says whether the static analysis report is a true positive or a false positive. Now the challenge is for new bug reports, the new bugs that are reported, can we automatically label them? Because for that we don't have the benefit of version I and version I+1. Now in my current version, this tool has reported it. So based on the historical data, can I predict whether this is a true positive or a false positive? So again, feature engineering has been done here using the different facets of the code to learn what would constitute a true positive, a true bug by the static analysis tool, or a false report, false alarm. So, and once this was done, they used traditional machine learning algorithms like decision tree, random forest to learn the model. The primary assumption when coming up with features was that the complex code is more likely to have bugs, and it is more likely to be classified as having bugs by a static analyzer, because it is highly probable that the developer failed to consider all possible implications of the code. So the intuition again is simple. Simpler code is less likely to have these kind of bugs, and the tool also will not report it. More complex code is highly likely to have bug, like a null pointer, dereference, division by 0, and so on, because of the sheer complexity of the code, and hence the static analysis tool will also report that. So the intuition is this complex code is difficult for other developers to understand, increasing the chance of introducing bugs and so on. So one indication of complexity of the code is the size of the bug trace, meaning when it reports a bug, it says, okay, this is this particular line called from this function, which was called from another function, called from another function, and so on. So a long bug trace indicates that the control passes through many functions, files, or packages. So the longer it is, more likely it is that the bug that is reported is a genuine bug. The location of the bug could also indicate the complexity of the code. For example, line number. The line number is indicative of the size of the file. If the line number is 1,000, that means it's about 10,000. It's a very long file. So on. So it's more likely to be more rather than a smaller line number. The column number also, if it's going into say column 100 and so on, it is more likely to be a bug because it's more complex, more nested, and so on. So these are all very interesting how those features have been engineered using our everyday intuition, what I as a developer would feel are problematic areas of code, using this to retrieve these features automatically and then let the machine learn as to what is important, what is not important. Depth of the line of the code indicates how entrenched the problematic code is. For example, if it's within an if, within an if, within an if. So this is a very deep condition. So this could indicate that it's highly problematic code and so on. Conditional statements that cause many branches of execution to emerge, and these can also lead to convoluted and buggy code. So one way they estimate the complexity is they count the number of times conditional statements occur, and also the occurrences of the or and conditions within the condition. For example, if A and B and C. So this is highly complex, the more ands or ors that I have. So these are all used to gauge the complexity of the code. So this is the set from the paper I have extracted this. So these are the different features they have used. We don't really need to know all of this in details, except to know that these are all used to determine whether to learn from the historical examples, version I and version I+1, whether the bug, static analysis reported bug was it. It's not about fixing the bug. It's more about learning whether the bug was a true positive or a false positive. Using this, when in today, let's say once this model is built and the model is learned, what it can do is, if I receive a new bug report from static analysis, I can know that this is a true positive. There's a confidence score, a probability between 0 and 1. If it says it's very high confidence that this is a true positive, I should look at it and perhaps try to fix the bug. If it is low confidence, then probably I can ignore it for now or prioritize it for later on. So that is, and they built this model. They, like I said, they used reasonably simple or they are common machine learning models like a random forest. And they're using this, they were able to, they manually verified, I think, some 60 of these bug reports. And they found at least in 41 or some of them, with a good accuracy, they were able to distinguish between the true positives and the false positives. So this paper again is is very instructive for me, because static analysis has been around for many, many years, from the 1970s and so on, 1980s. And the problem of was it would not scale to your modern software. So they introduced approximations, and with these approximations, a lot of false positives were reported, and the false positives, they effectively hindered or the usage of these tools. So AI kind of stepped in to help us kind of rescue it. Otherwise, we probably cannot use these tools now. So AI this is an excellent example of kind of AI helping us bridge the gap and kind of bring a tool that's very useful. Static analysis is extremely useful, because at the time of coding itself, it can tell you about potential problems. It doesn't have to go to the testing phase. It doesn't have to go to the customer and be reported by the customer, which is really bad. It helps. Always the motto is there's a shift left strategy in testing, meaning detect the faults as soon as possible. The farther along the cycle the fault is detected, the more costly it is to fix it, and so on. So static analysis is extremely useful. At the time of writing our code itself, it can reveal faults, but it simply could not scale, and it had a lot of these problems for false positives. But using reasonably simple AI techniques, we are able to kind of rescue it or associate it and use it in practice. So we have seen AI being used for progress static analysis to improve the quality, to improve the build times of Predict. They do better build in Google, in IBM. This is used for analysis, and in Facebook we also saw it being used for test selection. One final, if we have the time, I will go through one final work that is 1 minute, please. Yeah, I can quickly walk through this usage at Ericsson, right?
A quick time check, Giri. It'll be good if you can sum it up in the next 5 minutes, so we can pick up.
Okay, 5 minutes is what all I need for this work. Yeah.
Thank you.
So this is the work that has been done by another group. Again, this has been actually used in practice within Ericsson, and also paper. This was using AI to prioritize code review requests. So developers, especially senior developers, experts, we often receive numerous requests to review a piece of code. Typically, before a piece of change code is merged from a branch into the main or the master branch. This is very common practice. Like I said before, there are different facets or different weapons used to ensure code quality, testing, static analysis of code. Another arm of this is code review by experienced developers. Code review can detect problems that unfortunately testing and static analysis cannot reveal. For example, last December, there was a problem with the log4j library. There was some buffer overflow, SQL injection attack. Those kind of things, before we can test it and all, experienced developers can point it out. So code review is an inalienable part of quality assurance. But what happens is it is done, but we need to prioritize this. Often there is no prioritization. The reviews, they simply follow a kind of a first in, first out paradigm. That may not always be the most optimal prioritization. Manual prioritization can be done, but it can be tedious, time consuming, error prone, or it could be biased. I might, be biased towards reviewing code that I'm comfortable with, or kind of developers that I'm familiar with, and so on. So what we want to do is automate this. So these authors here, they claim that several different areas like prioritization, requirements, prioritization have used Bayesian networks, and they use Bayesian networks here for this software. So for this task, so again, feature engineering was done here, and these are the different factors that were used. For example, size of the change, the number of added or deleted lines of code, files changed. As you can imagine, if there are more files that are changed, or if there is hundreds of lines that have been added or deleted, probably that requires 4 eyes, meaning that requires more code review than a change that was, that just modified one file and one line, given a change that was one file, one line, versus a change that was like touched 100 files and maybe made thousands of lines of code lines were added. Probably that needs to be reviewed more. This is very intuitive. Similarly, age of the change, longer it has been done, we want to review it more thoroughly. Code change type, if it is internal refactoring, it is perhaps fine, not as high priority as for example, if it was a bug fix, we want to review bug fixes more thoroughly. Test verdicts, if the automated tests that were run, if they had failed, maybe this needs to be reviewed more thoroughly, and so on. Developer stats, if it's an experienced developer, probably we versus an inexperienced developer. If it's an inexperienced developer, we probably need to review his or her code changes more. Then if there are merge conflicts and so on. A lot of these features were used to build a model that could predict help prioritize. So what they did was these review requests are grouped based on the presence or absence of merge conflicts. Requests with no merge conflicts have higher priority, because with merge conflict anyway it cannot be merged. So it's better that the developer fixes those merge conflicts before coming back for code review. Then the review requests in each group which have no merge conflict or merge conflict, they're further grouped based on the type of code change, whether it's a trouble report fix, a new feature, or a refactoring. Priority is of course given to trouble report fixing, to new features, and then refactoring. Then the final step is to prioritize within each group based on the probability. Using the previous table of features, they used in Bayesian network, anything, even a regression model could be used to predict a probability of merge. And the higher merge probability means higher the priority for reviewing that. So this is a kind of an automated way to, if I have tens and hundreds of code review requests, automatically prioritize them for me so that I can, give the necessary attention to the things that are important. So this was about it. It was broadly, I tried to cover both the kind of a high-level theoretical aspects of how software AI is used in software engineering, how we are moving to the next phase of software development, and I also gave some hopefully what were useful and practical examples of it being used in the industry. There all of these four things that I spoke about: test case selection, build time, static analysis, and code review. All of these have used AI to improve the process, and they have been used in these respective companies: IBM, Ericsson, Google, and Facebook. So where can I find the latest trends if you want to know, if you're interested in this, especially AI applied to software engineering? The place to go is the software engineering conferences. There are these conferences, international. If you do a Google search, you'll find them: International Conference on Software Engineering, Foundations of Software Engineering, Automated Software Engineering. Each of these conferences has an academic track where the research scholars present their work, and an industry track where industry practitioners like me present our work. Then there are these public pages: the Ericsson, Microsoft, Google, Facebook has their engineering page, and so on. Then often there are LinkedIn or Medium articles by the company or people working there. For example, I have a colleague, friend at Uber. He regularly publishes, advertises his work that they have done, like, for example, tech debt reduction and so on LinkedIn. So a lot of these different forums, you can use to see how companies are applying or using AI for software engineering. Yeah, that kind of concludes my presentation. Hope it was not rushed, and hope you found it somewhat useful at least.
Absolutely, Giri. Thanks a lot for the insightful session. We definitely have a lot of questions, and we encourage our audience to keep dropping in their questions in the chat box to keep the conversation going. And for the ones asking for the presentation and recording for the session, please drop us a note to events@zinnov.com. We'll keep you posted on the same. With that, we'll get started with the bunch of questions that we have for your session, Giri. I think one question you have already answered. I think quite a bit of them are asking about where can we go ahead and read about the latest trends. I think through your resources slide, I think they would have got an answer for that. But the first question that we have is in terms of what is a proper roadmap to get started with AI/ML, right? Based on your experience.
Sorry, AI/ML in general, or what is it?
In software engineering.
No, what's the end goal? I mean, do you want to learn about AI, or do you want to know how to apply AI to software engineering? What is
it's about applying AI/ML. Let's assume there's a company who are just getting started with the entire journey, right? So where do you think will be the starting point for it?
Yeah, like I think these conferences, I can provide links offline as well. You just do a Google search. Don't use the abbreviation ICSC, because I think there is some Indian board, right, as a school. So if you use this International Conference on Software Engineering Industry Track, Software Engineering in Practice, you'll find a bunch of the latest accepted papers and so on. I can send some sample links as well after this session is over. And using these links, you can find out what is the latest. All these top companies, they invariably publish then I don't know. They're not highly secretive and all. Maybe there's certain things that they keep secret, but the things they advertise a lot of things that they do, like Facebook, for example. Like they said they use testing. All companies do testing, right? So how can you use? You can use Facebook's ideas, for example, and you can adapt it to all the things that all the features that they use may not be really applicable, but you could read those papers. And a lot of times what happens is there is in software engineering, at least these conferences, there is this concept of open science, meaning I cannot simply publish a paper and say I achieved this. Other people want to replicate it. So they have this open science concept where they, for example, this IBM paper that I was talking about, their data set is available, their machine learning models are available. So if you have reasonable AI know-how, you can use it, apply it to your own problem in your company for sure. So you can read about that paper, adjust the features accordingly, because some of these features may or may not be relevant to you. But you, by reading this, you can apply it. And we are also doing that. We bring the state of the art to our companies. So that can be done with these. I can provide the exact links for these. These conferences happen every year. So you go, and these are like attending these conferences involves a fee, but browsing these links on the web page, the list of accepted papers and all, reading that actual paper. So many times what they do is they offer a preprint. You may know this web called Archive. They put up their papers there. If you do a Google search for the paper, the archive link is there. Or if you write to the authors as well, many times they are keen to kind of evangelize their work and so on. So they will give you the paper. So all of this it can be adapted by these. I can provide more exact links, but you can do all of these.
Great.
Yeah.
Thank you so much, Giri. I think probably we'll connect with you offline to get those links from your end and share it with our audience here. And we have quite a bit of questions around the testing and as well as the QA side of it. Based on your experience, how do you think we can implement AI in test automation frameworks, right, for testing of web applications?
Automating, so that's kind of a slightly what is this, like you want to automate the end-to-end testing or repair the test cases, what is it like? So I have seen work that uses, for example, what might happen is sometimes the developers, they make changes to these UI elements. Instead of login, take a simple web page login. You could have username, password, and then the test case might say click login. The button was probably named login. Now it's changed to submit. But by using the environment around it, for example, it is closer to the next button is cancel. The element above it is a text box called password, and the element above it is a text box called username. You can kind of co-locate it and then say, okay, this button called submit was what was the previous login button, and hence you can automatically repair test cases. So there's a lot of work using. You can generate different paths and so on. There is some work, and I can again provide the links that try to automatically generate these test cases. So that is one area. Previously, we used to use Selenium and all, but now that used to be a record and replay kind of things. But but this for this also AI has been used.
Got it. So there was a code generation use case that you were referring to, right? I think each people write code in a different style and different time and the space complexity. How do you think AI is going to understand the semantic meaning of logics behind each of these algorithms and map them into the line of code?
That's a good question. Different people write differently, of course. Even some simple stylistic patterns, like if you're writing C++ Java, where you put the braces, like where you put it on the same line or the next line and so on. But the ultimate goal, see, what the advantage of AI is, there are so many examples here. So in India, we talk about some demographic dividend and so on. I'm not sure whether that really is true. But in software engineering, at least, there is a lot of dividend we have in terms of code samples, the open source. There are so many samples out there, so GitHub, previously SourceForge, and so on. So the very common style, common and correct style will be picked up and it will be coded for sure. So yeah, it is possible. It won't be 100% like it. I don't think developers will ever be replaced. That is, I just don't think that's going to happen. Just like these self-driving cars, I don't think you will have a situation where a person need not drive the car at all. But a lot of assistance will be there. Bulk of your code, the mundane parts and all. For example, if you write a loop, the IDEs would help. They would put the braces, the opening and the closing braces for you. But for now, maybe the IDE will also write the loop for you for int I equal to 0, I lesser than some array, I plus plus, so on. And then you have to write the actual logic or the API to be used, complete code completion. A lot of this is common. So from the various examples we have, thousands and millions of code examples we have, I'm sure the right one will be picked up.
Got it. Thank you so much for that, Giri. And we're also hearing about AI going to replace QAs in future. What are your thoughts on that?
Sorry, what is that? AI going to reclaim what?
QA.
Quality assurance.
Yes.
It is, right. It is now being used to see, AI is ubiquitous. It's there in all fields, all aspects of life, and sometimes frighteningly so. If you browse Google for something, and suddenly out of nowhere you'll see an ad for it. So it's almost like some big brother is really watching you and so on. Here also, AI is used, like for example, we saw that it is heavily used for this test case selection prioritization. Code reviewer, this has been the latest trend that I'm seeing now for the past this year and the previous year in these conferences. Code reviewers are kind of an exclusively experienced developers like me, an activity for us. We were going to review the code and give comments and so on. Now that has they have used deep learning because of this Garrett and all. There are comments to this particular line of code and so on. So AI has come. It's generating the comments. It's generating the review comments, the static analysis. I won't say it will take over completely. You need that little bit of human intervention, but it is already heavily into that space as far as I see.
Okay. So as we are talking about the QA, we will also talk about the AI. We are also hearing about AI will automate jobs and everyone will go to a no-code mode. Do you think AI will snatch jobs in future?
No, I got that question in your fireside chat as well. It's a very interesting question. And if you, I was not around, but maybe 30, 40 years ago, if you remember when, if you read the papers and all, there was a lot of these banks and all, there was a lot of opposition to even computers being brought in. They said it will remove all the banking staff. It will render them, jobless. It will lead to high unemployment. All that in India, at least. I don't know about abroad. So these unions, they used to strike and so on, right? They opposed computerization itself. But now we have seen that it is not. Humans are as much. There's so many new things that have come up. Similarly, even with developers, the developers will always be there, I think. To at least validate that the code that is generated is correct, it is understandable. So if somebody has to fix a bug, so he or she can fix it and so on. So developers or testers, they will not go, except the skills will change. 20 years ago, I think most of us were software engineers by default. Our titles, designations were. Now most of us are data scientists because we are analyzing the data, building models upon it. In future, it will be something else, but I don't think all the people all will be rendered, defunct or something like that.
Okay. So based on your experience, are you aware of any AI open source tools available for the test case selection in order to customize the test case selection requirements?
I think that the Facebook one was, I don't know if they have actually revealed it, but the paper and the features they have used are fairly simple enough. I mean, all the features may not be applicable at your particular company, whichever company it is, but using that, you can build the model using your historical data. And I don't know if there's an actual open source tool that does it, but you should be able to build the model if you're reasonably good data scientists.
Got it.
And and more importantly, you should have an existing database or a historical test execution data. Like this test case, I ran it, say January 1st, it passed, January 2nd, it failed. If you have a good catalog of all these things stored, it should be reasonably straightforward to build a machine learning model to predict.
As we talk a lot about the privacy of data, how do you think the implementation of AI in software engineering ensures that the protection of the data is being taken care of?
I'm not highly into that area. That is not my area of I've not worked exhaustively or a lot in that area. So please take my answer with a pinch of salt. Uh, there are guidelines that have been there. The European, since I work for Ericsson, I know about there are this GDPR guidelines and all. Hopefully it will, but in India, I see it's misused a lot. Like you get a lot of phone calls. I don't know how people get these numbers and so on. So I don't know. I think AI in Europe with these guidelines and so on, with the strong regulatory mechanisms that they have, Europe and the Western world. I think it will. They will ensure that AI does not overstep its bounds and reveal break privacy and so on. But in India and all, I'm not sure how it will play out. Honestly, it could lead to a lot of misuse as well. A lot of the data could unfortunately become more easily available. But once again, this is not really my area of expertise. So please take it with a pinch of salt.
Absolutely. You know that 80% of the companies are smartly investing in AIs, and nearly 47% of digitally mature enterprises have defined the AI strategy. As you can see, the cost involved in the implementation of AI is huge, right? How difficult was it to get the business buy-in in the initial stages, and how do you think as a company you can justify the ROI for the investment made?
I see the historically I cannot speak about, because I don't know how whether it was sold very well by the people or what it was. But I feel the return on investment is justified. See, I see it as more of an automation of the software, the entire life cycle. There's a lot of mundane things, very commonplace things you have to do. So AI, especially you can automate those things very much. Then we can focus on, for example, in testing, I can focus upon the corner cases that AI probably did not generate the test cases or did not select it. Similarly, in code review, if I don't want to be commenting on for somebody telling him, please ensure that this code line is say 80 characters, because more than 80 means your eye. There are studies that show you'll have to scroll, you move your eyes around. So that's less productive. So I don't want to be writing such comments. Rather, I want to be focusing on important parts. So if AI can, automate a lot of these common parts away, then we can focus on the really important humans. The experienced humans can focus on the really important things. So that, I think, when we have seen all of these companies also, they're not simply, it's not an empty boast. When they're publishing these papers, you can be assured that it is those things are in place. At least they were in place for the duration of the time they published the paper and so on. All of these Facebook's tools, Google, IBM, all of these are used. So there is a good return on investment, and they are using it. Initial cost might be slightly high. Yes, it will take some time, manage what was already done. But in the long run, I feel that it is entirely justified.
Okay. What are your thoughts on using AI for building low-code and no-code platform? Let us know if you have any use cases that you have seen on your experience.
No, I don't know. I have not seen it on our platforms, at least within Ericsson. At least I don't know about that. But I can kind of read about it and answer for sure. But I don't know. I don't have any practical experience on that at all, unfortunately.
Got it. So with the interest of time that we have in hand, Giri, we'll take the last question here. We also hear a lot about the carbon impact of the infrastructure around the big tech development of AI is also significantly due to the intense energy used, right? What are your thoughts on the same?
No, I mean, yeah, it's more of honestly a first world kind of a thing. Like there are so many other carbon emission, those kind of things that are happening, that this is really, yes, it's nothing is free, like all these servers that Google uses, or all these, it's undeniable that the deep learning models, they have benefited tremendously, and they really require they're highly, extremely resource intensive, like never before seen, because unimaginable doing it on our laptops and so on. That is very much true, and they take a lot of resources, yes, and so resource consumption means the carbon footprints are there. But compared to the other things in life, like the cars or those kind of things, maybe we should solve those first compared to this. I don't know if, we cannot run these models on low, maybe that will be the next area of research, how to reduce the usages. Already for mobile apps and all, there's a lot of research on classifying the energy needs, classifying them as green or not green, and so on. But comparatively, it is not as high as the energy usage or wastage in other aspects of life, I feel.
Thanks for your insights around that, Giri. I must say that we still have quite a bit of questions to go through, but with the interest of time that we have in hand, unfortunately, we have to end this session right here. To the ones who are still asking us a bunch of questions, please drop us a note to events@zinnov.com. We would love to take these questions offline. And that's it we have for you today. It was an extremely thought-provoking session, and we had quite a bit of takeaways. Thank you so much once again, Giri. It was an absolute pleasure to host you. And to the ones who joined us today, hope you found our session useful. Thank you once again, and see you in our next Zinnov's webinar. Take care and stay safe, and have a great weekend ahead. Thanks a lot.
Please send me the questions. I'll answer offline as well.
Yes. Thank you, Giri. Thanks a lot for your time.
Thank you.
Thanks, everyone.